Oh man, Miss Pugliese, I am so tired. I don't have the energy for anything.
Well, Mr. Palmer, we got to change that. How about an egg?
Well, that would be a great start if every morning I had the right amount of energy, that's for sure.
Right, so we can change this egg into energy for you and some matter for you as well. But in order to do that, we've got to add energy to that egg or any change we want to take place. So you've got to add energy to make it happen.
When we talk about change, in the world of chemistry, we've got a couple of different kinds of ways that we can look for change. I mean, there's things that just change a little bit and can be easily returned, and that we can talk about first as a physical change.
And a physical change is one classification of change we talk about in chemistry because we care about whether the matter changes its identity or not. In other words, does the chemical formula change? Is it the same stuff before the change and after the change? For example, boiling water. If I put some liquid water in this container right here on the hot plate and I get it to at least 100 degrees, then you will start to see the water boil. Those bubbles that you see forming in there, that's just the steam coming out of the water. So water is H2O in liquid form. Water is also H2O in steam form. That is an example of a physical change from liquid to gas because the gas phase of water is still H2O. The molecule has not changed its chemical identity.
Wow, so that's water in those bubbles in the small of a boiling pot, huh?
Yeah, once it gets to boiling, it's not air. That's H2O vapor.
That's super cool.
But if I wanted to change H2O and split that molecule apart into its hydrogen gas and oxygen gas, that would be an example of a chemical change.
Wow, and how much energy would it take if it's 100 degrees to make it just change to gas? What would it take to tear it apart?
Well, to break that molecule apart into the hydrogen and oxygen gas, you'd have to get this hot plate up to 2,000 degrees Celsius, which it can't even do. So lots of energy required, a lot more usually to cause a chemical change versus physical change and changing the chemical identity of the substance.
And when it's done, it has something completely a different look or a feel to it. It would have different character when those chemical changes happen.
Right. Those properties before and after will change with chemical change. As well as physical change. And we will help you distinguish between physical and chemical changes by looking for qualitative signs, which we'll do next in our demonstration.
Cool. Well, let's get down to seeing what kinds of change we're talking about and what we can look for to determine if something's a physical change or if something's a chemical change.
Right, so we're looking for evidence of chemical change here. And why don't we start off with the first beaker you've got over there?
Excellent. Without saying anything other than I want you to make some observations. And when I take this, which is just an Alka-Seltzer, and I'm going to put that into the water, we're going to look for evidence of some kind of change.
I see bubbles.
And that's a great example of one way that we know a reaction is happening in a chemical difference. It's making something different chemical. That was a solid. This was a liquid. Now we have gas that's coming off that is happening quite quickly.
And that gas is coming off of the tablet. It is created newly in the solution. It's not just there because Mr. Palmer dropped the tablet in there and air got stuck. This is newly formed bubbles.
Right, and this bubble is not the same as what we see in boiling. These are not the same material that the water is made of, nor is it the same material as the tablet. Okay, next one. Let's pull this solution out. Okay, take a look closely at this. I'm just going to put a drop of this other solution in.
Notice how they're both clear.
Yeah, let me get my hand
Clear
up there so you can see that. Let's just put one drop. Wow.
Wow, lots going on in there.
I love the way that looks.
Why does it look like streamers falling down? What is the character of that yellow stuff?
Well, as I talk with students, anytime if I can't see through it, that's actually not a liquid anymore. It's not clear, even though clear yellow solutions are possible. That is a solid or a precipitate. And I'll put a second drop in.
So that's a precipitate because you started off with two liquids and suddenly we've got a solid. If you took a microscope slide and put just one drop of that yellow substance on the slide, you could see that there's these little crystals, and crystals are a solid. Okay.
Excellent. I'll finish by just giving that a tweak so you can see what that looks like. And if I let it sit, it would go and settle on the bottom because those are little particles of solid. Awesome. Next, let's take a look at this material. This is just a standard candle. And the first thing you might notice in terms of changes, what happens to that nice white wick that's there?
Well, I see it changing color.
Absolutely. That change in color is a great example, again, just like we saw previously. Now, you may think, that's the only thing that's really happening. I don't see much going on. If we look closely at this, you'll start to see that it looks like a darker color that's right around at the bottom of the wick, and it'll start to grow. Matter of fact, if I look, it's sort of got a wetness to it that's right around the wick, and that wetness is starting to get bigger and bigger. So that's a great example. That heat energy is interacting with the wax that's there and causing a physical change. How do I know it's physical? Well, I could blow it out, and that would go back to that nice, solid-looking wax. Now, that's just one of the processes that's going on, and you may say, well, that's all there is. But if I'm going to be sort of creative, I can use this spoon, for instance, and I can look to see if there's some other kinds of material that's going on from that flame. If I just put this on the bottom here, and get that nice and close, you can see I can make some changes above that.
I think I see some smoke.
Yeah, there's some kind, and it's a dark colored kind of smoke, so that when I go on the back here, you'll notice that you may think, did you just burn that spoon? And I really didn't. That's just material that came from the flame. So if I wipe that, you'll see that I have material that's been collected on that spoon, and that is from the flame, and that is normally not there because normally we don't catch it in the middle of a process. So this is actually incomplete combustion. It's taking that wax material and making something that's black like this, which if you've ever made a barbecue, you can know that those charcoal briquettes are made of carbon. And so carbon's coming out of the flame. There's carbon coming out of that flame. Matter of fact, if we wanted, we could even determine a couple of things. If I put this over the top, you might notice that as we watch, this flame is going to change and get smaller. I'll even move this around so we can see that. And as we continue to watch that, it's a little smaller, and it's starting to get smaller noticeably. Also look around the sides. Give it just a second. Usually right when it's getting towards the bottom, it gets the most. I'm starting to see what's happening on the sides there. I can see it if you're looking closely.
Oh, I see it. It looks like it reminds me of morning dew a little bit.
Yeah, and so as a matter of fact, as that goes out, there's something in this container that's going into the flames that eventually, when we're done and that goes completely out, okay, that got used up inside, and if I put my fingers in there, I can feel that that's wet. So there's water coming out of the flame. We saw there was also carbon and water as part of a change because that material going into the flame was the wax of this candle. All right, let's take a look at a different change.
Oh, very quickly, the energy change is a sign of chemical reaction, and sometimes the energy shows up as light, like you saw in the flame, and sometimes as simply heat, which you can also feel from the flame. But one thing to keep in mind, that some of the wax melted, and that is a physical change, but some of the wax was consumed in that burning, and burning is always a chemical change. And our evidence of that wax being consumed and being converted to a different substance is the black substance, the different carbon compound on the spoon. But in that case, matter was conserved. So even though the wax was burned and converted to something else, if we took the mass of all the starting material and then were able to collect all of the material that burned up and left from the candle, we would see that the masses were equal. Same with energy.
It's easy to get confused because it seems like that matter disappears. It just goes into molecules that are transparent. They don't let light, they allow light to go through it. So we don't think there's anything there, but that's why we were taking the spoon to catch some of those.
Right. So you may have noticed in all of these changes so far, you've seen a color change in one way or another. Maybe something was white, went clear. Maybe stuff was clear, went yellow. Or the white wax was consumed and turned into some other black compound. So a color change often indicates a chemical change. But be careful. It's hard at first when you learn a new rule. You want to just apply it to everything that you see. What if I took food coloring and I mixed it in water and I've got green water? Is that a chemical change because I see a color change, or is that a physical change? How do I know?
Well, and one thing we talked about can easily go back, but once these two get together, they're so mixed, it's like throwing cards on the floor. It's hard to get them all back together. So let's just take a look and see if the substance is different in some ways that we can test or make some observations or reasoning. Then we can say then indeed a chemical change has happened.
Right. So if I wanted to get green food coloring water separated out. I could separate it easily by boiling the water and collecting the water that evaporates off, and that's just the H2O, and the green dye would be left behind in the container. So I can separate it with a physical change. That's how I know a chemical change has not happened. So be careful with things like color change and bubbles, and think about the other evidence that is there that indicates that it is a chemical change or not. So I've got a purple solution here. I'm going to add a clear substance to it, and we're going to look for evidence of chemical change by color change. This is clear. Going into the purple substance. Did you guys see anything? Did you see anything in there?
You know, I did, and it's even still changing. Now it's just set up as a little different color than we started.
So I started with purple. I added the substance. It's a little bit different color. I'm going to add a little more and see if I can get more to happen here.
Wow,
okay, that's
cool.
significantly different. Now it's
Yep.
blue.
Mm-hmm.
And it's still changing, and it's I don't know by looking if I can separate this, because, well, I know what this stuff is, but I'm not telling you.
Right. Okay.
So there's got to be some other way for you to know whether this is physical or chemical. Sometimes you can't rely on, I'll check that out. Sometimes you can't rely on just looking alone. You might need quantitative evidence. And in that case, we can use sensors. Maybe we can look at pH or temperature or conductivity change to look for signs of change. Continuing on, I'm putting more and more of the substance
That's
in
kind
here.
of greenish, aqua.
Check this out. Let's see. Make some predictions about what you're going to see next. I bet you can predict the next one. I bet you were right about the color you're going to see.
Wow.
Another one. Another one. More. And more. I'm just going to dump the whole thing in there now. Because that is the end of the color changes that we're going to see. This was the chemical indication because I know that this is an acid-base reaction. And when I mix an acid and a base, that is called a neutralization reaction. And I've thrown in something to make that apparent. That is called an indicator. It shows you that the pH is changing when pH changes because of acid and base coming together. That is a reaction, chemical change.
There's cool biological molecules that help us to determine what's inside and happening that we can't see. Just like this spoon was good at capturing something we couldn't see.
Right. Okay. Now let's make that egg so that you can get your energy back. Okay?
I was waiting for some good energy.
All right. So here's a healthy piece of energy here. There's energy and matter in here. We're going to rearrange the bonds in here, hopefully, to give you some of the energy out of this substance. So I'm going to crack this egg. Is this cracking? Is that physical or is it chemical change?
I suppose it's a little hard to think, but I think with a spoon or something, I could get that back in there and maybe some glue or something. But it doesn't change the nature of either the shell or the egg inside.
Right. So it's not easy to put the shell back together, but it is still eggshell.
Mm-hmm.
So that's, and this is still egg white and yellow egg. Now I'm going to dump that into the cup. So you like your egg scrambled?
Yeah, absolutely.
Okay. So I'm going to whip it up first. Sorry, I don't have any milk to put in here, no omelets today. Well, if I wanted to separate this, could I do that easily?
Not easily, but there are kinds of things that might filter one versus the other or some kind of way to make those come apart.
Yeah, it's still this yellow egg and egg white is still, they still have not changed their chemical character yet. I don't see any signs of change. The color changes just because I was mixing, and mixing is a physical change.
Right.
Well, now I'm going to put it into the heat here and see what happens. Just a little bit. And we've added a circle so that you can see.
So you can still see through with the egg yolk and white mix.
And turn up the heat a little bit. So I'm going to spread it out to fill the entire container.
You can see through it. It's translucent. It doesn't allow light all the way through, but it somewhat blocks it. But it is see-throughable. I can see the black circle as you can look on.
Okay, here's the black circle. Keep an eye on that. And actually look at right here.
Right. I noticed that some parts of the black circle are starting to look more
opaque.
Yeah, like a fog is starting to form over those. As a matter of fact, I can see that fog is becoming even whiter.
It's actually becoming more solid as well.
Absolutely. And so it's allowing light not to pass through.
Okay. And as I stir in here, I see that it's all turning solid. and it smells good. I'm gonna waft that smell up to where I can smell it. So I have to get too close to the heat here. This is
And that process is important because not every chemical reaction that we can see, this is a chemical reaction. As you see, the texture is changing, the color is changing. It's going from a liquid to a solid that doesn't change back.
The odor's changing for sure.
The odor's definitely changing.
You can smell it.
And so that wafting process is important. If you have chemical sort of tests that we'll do, sometimes those are very strong smells. And so that's where it becomes really important. And what you want to do is bring some of that smell towards you, and it will dilute that as well. So if you want to see the process of something when we're testing a test tube, here's what a wafting would look like for that.
Do not do this.
No.
Never do direct smelling over the test tube. You want to waft the odor towards you, keep it a distance, safe distance from your nose, and move the air towards you so you can smell whatever may be in there. Okay, I think we've run through all the signs of chemical change, but sorry, Mr. Palmer, there's no eating in the lab.
No, I can't even have my egg. Well, I'll have to get a good breakfast before we start next time.
Let's talk about safety. So you see that Mr. Palmer and I both have our goggles on. We're not wearing long sleeves, but if we had them, we'd roll them up and make sure nothing was dangling, including my hair, which is tied back, and I have no jewelry hanging that could get into any liquids or anything.
And that includes a school, like an ID tag or something like that. You can put it in your pocket or on your desk next to your books or something.
What do we got here?
All right, now you're also going to see that we're starting off in chemistry. We have some solutions. These solutions are just colored combinations of liquid and whatever else that's mixed in there. But you want to treat them as if they were something that could do some damage to your hands if you got it on there, or it might be something you want to always limit your contact with chemicals that we use in the lab. Even if it's something that's familiar, that you might think, oh, that's nothing, I deal with that every day. Treat it in a lab as if it were something that could cause either some harm or some change that you don't want to have happen.
And in today's investigation, we're going to be adding sensors and sensor data to get some quantitative data to evidence to add to our qualitative observations and come to some conclusions about the types of change we see, whether physical or chemical.
Now, each of those is wonderful so that we can, sometimes it's hard to see some of those changes because they happen in the visible world is not exactly like what we saw in those first examples. But I'm going to start off with the pH sensor that you can see here. What you're going to notice is that the end is stored inside of a little vial here. The vial itself has got some liquid in there that keeps the end sort of fresh. Glass is what's measured at the tip. I'm going to pull this open, and when you take this apart, what you're going to do is just unscrew the bottom of this so that the capsule can be put over on the side. And then for this, I'll put this back down so you can see that. We're going to move this so that it's higher on this, this shaft here, so it's easy to keep track of. Otherwise, it sometimes sort of gets displaced if you put it off on the side. And it's a good way to keep looking at those. Now, the last thing I'll say is that we're measuring how much acid is in water through this little glass bulb that's at the bottom. And it's acting sort of like a sponge. Even though you think glass is, you can pour water on it, it wouldn't sink in. It sinks in enough that it causes this ability, you see maybe a little wire in there, to be able to register that there's more acid in the water.
So when you're measuring with this instrument, you want to make sure that that's completely covered with the solution, like Mr. Palmer said. And a good way to do that is to look for the black ring here. And if you've got water up to that level, you're good.
Matter of fact, that continues with the other instruments as well. And you can show them where you're going to use those other two instruments.
Okay, I've got a conductivity sensor here, and this looks for charged particles that are floating freely in solution. And you may or may not be able to see the silver prong that's inside of that plastic wedge there. Again, you're going to want to get that completely submerged in water. If you can let the water level go at least past this notch here, then you're good. You've got everything. You don't need a whole ton of water or liquid, rather. Just go up to or beyond this notch. And the temperature sensor, this looks like you have to put the probe deeply into some liquid or solid, but actually the sensitive part is just the end of the probe here. So if you've got that covered just like these two, just the end, you're good to go and you're collecting data. We will demonstrate how to read the numbers off these while we're doing the experiment, and also how you must clean each of these probes as you move between different substances.
And you'll see that's why we have things like the water bottle that's here that will rinse them off. But you'll see that as we collect the data here in just a moment.
Well, let's get started with the investigation 3C, physical or chemical change.
I see our first step is just to make observations.
Right, so open up your answer sheet and record the observations. That is the color of solutions A, B, C, and D in table 1 on your answer sheet. Take a minute, pause the video, make your observations, and when you're ready to move forward, then press play. Okay, you should have the color of solution for A through D filled out in table 1. Now let's very quickly talk about the directions document that your teacher might have shared with you. Mr. Palmer and I have been following along these steps in the procedure here, and you can follow along as we do each investigation. But I wanted to point out, since this is our first experiment with SparkView, I wanted to point out how to use that software. And if you have not yet downloaded the software called SparkView, pause the video now and look in the App Store and download it and get it on your device. If you have a Mac or a PC, talk to your teacher so you can get a copy of that. Hit pause if you need to, otherwise let's move on from here for SparkView. So in the procedure, we've already done step 1. We've got 4 clean 50 milliliter beakers labeled A, B, C, D. We filled each with 25 milliliters of each solution. We've asked you to do step 3, record the color of solutions in table 1. And now we're on step 4, where it says to open SparkView and open the 03C physical or chemical change lab file in SparkView. Your instructor probably shared that file with you, so you would have downloaded it. And I'm going to show you how to open that file. So let's go to SparkView. When you open SparkView, it looks like this. And you go to the button that says Open Saved Experiment and find wherever it is you saved that lab that your teacher shared with you and click Open. Now, mine's going to open with no data in it, but when you open yours, there should be data from us doing this investigation right now. We've already connected the sensors, and I think we're ready to go.
Absolutely. The first property we're going to study or look at and make observations for is the temperature. Now, each of these have been sitting out for a little while, so I'm going to go ahead and just put, like we said, just that end is enough to get the reading for what's in here. So I'll put this across.
I'm going to start collecting data.
Only time I'd make a mention is if this is sitting on a hot plate, you don't want to set it on the bottom. But if it's just here, I think it's going to be fine. We see we have a temperature there.
While that's stabilizing, we can actually measure more than one property at a time. Would you be able to hold all of them? Okay. You got this one?
Yep, I'll do both hands.
This one's the pH. And we did rinse all of these sensors before putting them in solution A, and we will be rinsing them again after we bring them out of solution.
Excellent. And what we'll do to record this for you, if you want to cross-check these, is we'll just save this.
Okay, in a second I'm going to hit stop. I want to point out how to read the values on the sensors. So Mr. Palmer was holding the sensors in there. To me, these numbers look stable, even though the middle number for conductivity is switching between 8, 9, 10, 8, 9, 10, 8, 9, 10. No, it's not stuck on any one number, but those numbers are very close to each other for that measurement. So if you hit stop, you can be sure that you're okay with whatever that reading is. Okay, so I hit stop. So we're going to say for solution A, the temperature was 23.8 degrees Celsius, and there are 3 sig figs in that number. And as Mr. Palmer pointed out last time, if you have a digital reading, you can use all of the digits that you see as counting as significant figures. Conductivity is 9 microsiemens per centimeter, and the pH is 6.9.
Fantastic.
Okay, so we've got that. While Mr. Palmer cleans these sensors, watch how he cleans all of those sensors, and being careful to get into the nooks and crannies on the conductivity sensor and the pH sensor, and also dunking in large volume of water. This is an option to do the extra deep rinse, but it does help to get better
results between each time.
Right, better consistency as well. So I'm going to create a new page in the SparkView file. Actually, I'm going to rename the page for solution A. That way, when you open the file, it will say solution A. I'm going to create a new page for temperature, conductivity, and pH. And I'm doing that so we can have one page for each beaker. And you'll see that it has the last measurements we recorded. On the last page, I'm very quickly going to rename this page Solution B. And are you ready?
Absolutely. So before I transfer these, even the water on here can have some impact on the next solution. So I'll just give it a couple of flicks there, and we're going to move right on into this next solution.
I'm going to start collecting data.
Give it a little bit of a stir, and then I'm going to let it sit.
Okay, and as you're watching, if you're watching the numbers in SparkView, you see that they take a minute to stabilize, and they are going to move up and down a little bit. But when they seem to be cycling around the same values, then we can consider that stable. I'll give it just a few more seconds because maybe we might see a little bit more change. I think that's pretty stable.
Oh, that looks good.
Yeah. Okay, I'm going to hit stop.
While she makes changes for another page, I'll rinse these again.
Next is solution C. Okay, I'm ready when you are. Ready?
Yes.
Okay, I'm going to start collecting data. Wow, look at that conductivity. Do you see that number?
Yeah.
It's anything that you see over 20,000 microsiemens per centimeter. We call that being railed, or if it's reached its maximum value. It's such a high conductivity that we don't know if that's the actual reading or if it's something above that reading. So keep that in mind. When you see a value 21,000 plus on your conductivity sensor, it's railed. That's the only one that's moving right now, so I'm going to hit stop. And we'll just keep those values. You'll notice that the pH and conductivity are also significantly different than the other two solutions, but temperature looks about the same, which makes sense. They've all been sitting out at room temperature. I'm going to build the next page.
Especially with the saltiness of that, or the amount of conductive species, I just want to make sure I get a good rinse, and that won't then be around for the next solution.
And you could tell that there was something conductive in there because the conductivity was high. Even if we don't know what it is, we can know the properties from the sensor. I'm going to hit start. We see the same thing. We've got a railed conductivity in that clear solution there. Oh, the pH is very different than the other clear solution, but the temperature is similar. We're going to give it a second and see, because I see temperature changing a little bit. Let's hit stop. Okay, I'm going to clean those, and I'm going to rename this page. I forgot to do that earlier. Solution D. Next, we're going to combine solutions A and B together. And then when we do that, you'll record your color for solution AB in table 1, and we'll record the measurements for that combination of substances. And I forgot to build my next page. Let me do that really quickly. And we're going to use the temperature sensor to stir to make sure it's mixed. Temperature, conductivity, and pH. And I'm going to rename this page solution AB. Okay.
All right.
I'll pour A if you pour B.
That sounds good.
Oops, wait. I forgot to hit start collecting data. Let's start.
All right.
And pour. Ooh,
that's cool.
Beautiful. Let's move these out of the way. Go ahead and stir a little bit, and then we can get the conductivity and pH. Go ahead and grab those other values.
Notice the way these are shaped, they kind of hold a little bit of water in them, so that's why I'm giving them a shape before putting them in.
Okay. Oh, look at the pH. Conductivity and temperature. I think we see a little movement on temperature there.
Yeah, pretty small, but it
Tiny.
is noticeable. Mm-hmm.
Very small.
And both of those conductivities were previously about that value.
And well, yeah, these all look very similar to the initial values of each of those initial solutions. So I'm going to hit stop. And so you should have recorded the color for AB in table 1. I'm going to build a new page here for when we mix solutions C and D. And you are looking for signs of not only physical change, but also chemical. You can consider each change you see and decide, do you think that what you see visually and what we measure quantitatively, could any of these be signs of chemical or physical change? Just to note that we haven't smelled anything. There's been no odor. I know you can't smell what we're smelling, but there's nothing to report here on odor. Are you ready to put C and D together?
Absolutely.
I'm going to hit start first.
Okay. You want me to do each? Or let's do that again. Okay.
Yeah, same thing?
Yep.
Ready, go.
Go.
Okay, go ahead and grab the other sensors. Interesting. And we definitely see differences between the individual values for pH and conductivity and temperature for C and D compared to when they are mixed. You're also writing the observation of color in table 1. And we are going to share this data file with you, or you can review in the video to get anything you might have missed. I'm going to hit stop.
Very cool.
Okay, and I think you're ready to answer those questions to complete your lab. Good luck.
Good work.